Of turbulence. Please welcome.
Thank you very much, Dishbab. Thank you for letting me give a talk. And I will try to use the computer and use the board to give you just some ideas about what is interesting in this, in my current research right now. So let me first of all outline the talk. First of all, I will try to give you, try to define the 3D Navier-Stokes equation, and then I will try to relate them to these shell models of turbulence, and then I will try to give you the motivation why we're interested in these shell models and what is the relationship with the Navier-Stokes. And at the end, I will try to give you some results, at least the most important one for now, and some others that are in current we are currently interested in. So let me consider the 3D Navier-Stokes. This is 3D Navier-Stokes, and it's on a torus. And I am writing it, so here, I mean, people that are working in Navier-Stokes, V is the velocity. This is a pointer that I am not used to. Okay, so V is the velocity, nu is the viscosity, P is the pressure, and F is the external force. As I said, this is in 3D. I will show you later the difference between 3D and 2D because it's very important. And 3D Navier-Stokes, I will try to rewrite it in the Fourier component. So V, if you write V as the a sum of Vk exponential ikx, k here is in Z3. Vk's are the Fourier component of the velocity. You write also the function, the forcing in the Fourier component also. You will end up with a system, an infinite system of differential of ODEs actually for the Fourier component, and where you see here Vk, k is in Z3 and V is with values in C3, so it has three components. It's very important. This corresponds to the Laplace, and this corresponds to the nonlinear term, and this part is related to the pressure term. It's very easy to find. It's just that you have just to compute the Laplace, the Laplace operator, etc. And this is, it's very classical. People find this equation very easily. So this equation, actually Professor Sinai was working in 2D, actually in 2D. He was working on this equation, the Fourier component of the Navier-Stokes. So the nonlinearity, you see here, this is the nonlinearity which is important. But you see here the nonlinearity, each VH in a certain sense is interacting with VL for all H and V such that L plus H equal to K. So all of them are interacting. So V1 interacting with V2, V3, V4, V5, etc. So they are all interacting with each other. It's a lot of interaction. Okay? Okay, now let me tell you at least what we are interested in so far in this particular talk is that for turbulent flows, I'm not interested in the fast transition, but once the flow is completely turbulent, there are some conjectures that have been made by Kolmogorov, and the conjectures is that the flow, at least the structure functions, these functions that I'm defining here, SP of R, which are averages, ensemble averages of delta VR to the power P, this is behaving like R to the power P over 3. This is his conjecture. Now let me just show you what I mean by these averages, etc. This delta VR is nothing else than the variation. It's V of x plus R, if you want, minus V of x. But I am using the fact that I can take x equal to 0 because I am using the fact that the fluid is homogeneous. And on top of that, I am using the fact that it is isotropic, so the directions are not important. So it's like I am doing this for the direction, so 0, here 0, and this, so isotropic, this means that I have the same direction I have the same intensity in each direction. And this is to the power p, and then you are taking an ensemble average, and this ensemble average, I mean, this average, this is important. I mean, in Navier-Stokes, we don't know exactly what to do with this, but if, for example, you are able to get an invariant measure, you can take the averages with respect to the invariant to one invariant measure, for example. So this is the idea. And Kolmogorov at that time, in 41, he conjectured that this will behave, so it will behave like r to the power p over 3. Unfortunately, this conjecture is not supported by experiment or by numerics for Navier-Stokes, except for the value p equal to 1. For p equal to 1, there is an agreement in the physics community and in the math community that it is true. Okay? Okay, so as you see this is averages, so averages are interesting here. So, I mean, we are not able to prove anything for Navier-Stokes in theoretically. Now, so at least physicists, they came up with this model, these shell models, to in a certain sense, to take care of this problem. I mean, you see, they are saying that we are going to get a model which is easy to handle with, and it is a model that will have the same property, the same statistical property of Navier-Stokes. So here I am not claiming that this model has the properties of Navier-Stokes at the analytical level, because it's not. At the analytical level, they are completely disconnected. At the statistical level, there have been some numerical simulation and experiment to say that the model that I am going to introduce now, that has been introduced by other people, I'm giving him here some references, and this model actually, it has been, if you see, Gledzer, Novikov, Sijia, these people are physicists, and they came up with this model such that certain properties of Navier-Stokes are still retained, still there. And we had to wait until 2007. Actually, Biferale wrote a very nice paper, which is a review paper actually. He's a physicist, which gives all the general results of these, shell models, but at the numerical and physical level. But it's full of very interesting, like open problems. So Constantin Levantiti, for the deterministic shell model, they gave, they wrote the first paper in 2006, where, and then following other papers, and they gave a lot of results for these, the infinite dimensional somehow shell models. And in 2008, in 2006 actually, with Flandoli and Barbato and Barsanti, we wrote a paper for the stochastic case where I am going to say some of the ideas that we got there. So let me introduce you directly to the shell model. First of all, the shell model is, first of all, it's an infinite dimensional ODEs, yeah? So UN will be our Fourier component, the equivalent for Navier-Stokes, but you see here that it's not anymore in C3, it's in C. So it's one approximation. The second approximation is that if you look at the nonlinear term, this is my all nonlinear term, the interactions are only between, you see, UN minus 1, UN plus 1, it's only between two neighbors. So it's only between, n plus 1, n and n minus 1. And it's this way, because at the statistical level, physicists say that, in fact, this is enough to say something about these, interactions. After, for turbulent fluids. Let me say something about, so this is the equivalent of the viscous term. Kn here, I should, so Kn here is the equivalent of K in Z3, but in my case here, Kn is just one-dimensional, and it is equal to K0, 2 to the power n. Usually it is even lambda to the power n, such that lambda is strictly bigger than 1, okay? And K0 is strictly positive, okay? It's some people call this, some models call them like dyadic models. So this is the nonlinear term, and here we are adding an additive noise for now. So sigma n is the intensity of the noise, and beta n is an infinite dimensional sequence of complex valued actually noises. Here un is complex valued, so my system is complex valued. And so this is my system, and the equivalent, you see here the equivalent of the structure function for Navier-Stokes. So let me just make one correspondence. R, which is in the physical space, remember R is in the physical space, the correspondence in the Fourier component becomes 1 over, I will write it like kn to the power minus 1. Okay, so everything you have to think now, I am not anymore in the physical space. Physical space, I have Sobolev spaces in physical space, etc. Now I am in the Fourier space. So Fourier space, this means that I have the Fourier component. And the structure function associated to the model, this is one particular model. Later on I will show you other models, but this GOI model, which is a little bit rigid, more rigid than others, the structure functions that I had defined before, the pre-structure functions, SPN equal to expected value, the averages that I'm taking now, I'm taking them with respect to the expected value of un to the power p. And the equivalent of Kolmogorov, we would like to see if this will scale like kn to the power minus zeta p, and we would like to know, is this zeta p, is it equal to p over 3 as Kolmogorov is saying, or because there is some disagreement in the physical community and they believe that maybe it is larger equal than p over 3, at least not for p equal to 1, for p different from 1. This is the, there are people that are working on this anomalous scaling. They are called the anomalous scaling. And now let me go back to my model. So now this is the model I'm studying. So now I forget Navier-Stokes for the moment. I am going to focus on this shell model, and I am going to try to prove some things on this, for this structure function, for this model, in the hope of, if we can prove something for these shell models, it's the equivalent of proving maybe something for Navier-Stokes. It is still very hard to prove anything for these shell models at the statistical level. So first of all, let me introduce you to the infinite dimensional, this is, I will write it in the abstract sense, etc. So I will define the space H, obviously, the Hilbert space H, the equivalent of the infinite square L2, the small L2. I will define the scalar product on H. I will define a norm. I will define an operator A, and I will define the norms in V as the sum of kn square un squared, the summation, the domain of A as this domain, and then I'm going to define the operator AU. Now remember that I am in Fourier components, so I'm not. So it's not the physical space. It's not AU in X, but it's AU the nth component. So the nth component here is kn square un. So this is my operator, and my nonlinear term, the nonlinear operator B, I can take this one. This is enough to have the same properties of Navier-Stokes, in the sense that I will show you now the properties of the Navier-Stokes. I still have to make sure that the following property is true, that BUV V equal to 0, the incompressibility condition in a certain sense. So this nonlinear operator has the property BUV V equal to 0. Let me show you just in general, because since I'm here, these other models, this is the GOI in the general case. What I showed you before, it's taking A, B, and A and B equal to certain quantities. So the nonlinear term, you can have many nonlinear terms. This is very rigid. This is very rigid in the sense that I will show you later what does it mean. It is a little bit rigid. There is another model, Sabra model, which is still like a shell model. It's a little bit different. And I forgot to tell you that when I write bar, this means this is the conjugate, since I am in complex value. And this is a little bit, so A and B are real numbers. So what do I mean by rigid? I will explain. But before that, let me tell you just the properties of this shell model. the operator A has this nice property, the coercitivity property. B is an operator which makes it a little bit better than Navier-Stokes. It's an operator from H cross V into H. For Navier-Stokes, we have a little bit less. We have this property as a consequence. We have these two properties that this is typical of Navier-Stokes, is the incompressibility condition. Okay, so these shell models, all of them verify this condition. Let me tell you, so I can write it in the abstract form, because we like abstract forms. I can really write it like for any PDE if you want, this equation, and now I am going to maybe give you some result, theoretical result. But this is not really my point. I will really rush to really what I am interested in. So let me just tell you two things about the difference between the two models, the Goi model and the Sabra model. And let me go a little bit about physics. And we don't care about proofs. Let me just go to the 3D Navier-Stokes. 3D Navier-Stokes, when I say 3D Navier-Stokes, I mean, actually when I say 3D Navier-Stokes, I mean when, let us take nu equal to 0. It's not Navier-Stokes anymore, it's Euler, okay? For nu equal to 0 and f equal to 0, in 3D, we have only one invariant, which is the energy. If I take the energy as 1/2 the integral, let me write everything in the physical space, of u x squared dx. This is the energy, and it is the only positive quantity, because there is another one which is the helicity, but we don't know what to do with it so far because it's not positive. It's the only quantity in Navier-Stokes which is conserved in a certain sense. In Navier-Stokes, when I say Navier-Stokes, in this one nu equal to 0 and f equal to 0. And this is the reason for which in 3D it's really hard to prove some kind of whatever regularity and uniqueness results. Okay? In 2D, Navier-Stokes, and this is the big difference between the two, again, when I take f equal to 0 and nu equal to 0, there are two quantities that are conserved, the energy plus, so energy conserved, plus there is another quantity which is the entropy, which is nothing else than, call it entropy, I don't know, I will call it like this, h equal to the integral over d of the curl, I should say curl or rotational, it's the rotational of the velocity. If you look at this quantity, in 2D, this quantity is conserved. And this is the vorticity. And actually, it's the main difference between 2D and 3D. And why I mention this, because it's the difference between somehow, it's just to mention this, between the Goi and Sabra. So the Goi model is, when you look at it, whatever I do for A and B, I can choose A and B such that the only quantity that will be, in a certain sense, conserved will be the energy. It's typical of 3D. It's the equivalent of 3D. For the Goi model, I can choose, it can be, equivalent for 2D or 3D. I can choose A and B such that I have this extra quantity, which is the vorticity, which is conserved. So it helps a little bit to prove some kind of more regularity or whatsoever. Okay? But in this talk, I am considering really the 3D, the Goi, because I am interested in 3D. So I am here. So let me, maybe I don't have that much time. Let me just show you, what is interesting in this problem. So, this is a problem now. You can think about: is it well posed? What about the long time behavior, etc. So I will just rush. Sure. This is a stochastic shell model, additive noise for now. So I can tell you that if W is a given h-valued Brownian motion on this filtered probability space, we can prove the existence of solutions, and I can show you the definition of what does it mean a solution. Obviously, it's all the time in the weak sense, for any given Brownian motion, we can find a weak solution in the following sense, such that this process is continuous, adapted with values in h. So we can prove this, there is no problem. we can prove, you know, for given initial condition, we can prove so the existence and uniqueness of this process. Plus, we have this nice. This is the equivalent, the energy equality, and this is somehow the energy inequality. Okay, I just mentioned these two because this, thanks to this this property in particular, I can prove some kind of existence of invariant measure for the stochastic case. So I will just rush to the. This is very particular actually for the non-viscous case. It's particular because it's different from 3D. So when nu equal to 0 for 3D Navier-Stokes, if nu equal to 0, and you take, if you want, even f different from 0, we are not even able to prove existence of global solutions. We don't know. Open, 3D, if indeterministic, yeah, it's open. In this case, it's very particular of this problem. If nu equal to 0, we are able to prove the global existence of solution for the stochastic and for the deterministic. But the uniqueness is open. And I think the uniqueness is open, and actually I think Flandoli in March gave some talks about another similar model, but where he proves some kind of uniqueness in law for similar model, but not this one. I mean, the uniqueness is not true in the deterministic case, but you can, but with a multiplicative noise. So it's, but for with an additive noise, the uniqueness is open. So, but what is interesting is that when nu equal to 0, you have global existence of a process for that equation. And the process is pure most truly in L infinity 0t with values in h, which is not true in 3D Euler equation. Okay, I can prove also for this model the existence of invariant measure. And as I told you before, I am interested in this invariant measure because I have to take some kind of averages. So these averages, I have to take them. It will be interesting to use them for this one invariant measure. I didn't prove the uniqueness of the invariant measure. So for this one, we can, for this model, I can prove that we have the existence of, so I can define this semigroup, the semigroup of transition associated to my stochastic shell model, and I can prove that this semigroup is actually Feller. And thanks to the continuous dependence with the initial condition, and then thanks to this, I can prove the existence of an invariant measure in H using, you know, using just tightness for a semigroup which is Feller. Yeah, and as you see here, this is I mean just for the proof, I am using this. You know, this expected value that I proved before, which actually the integral between 0t of this guy, I proved that it was bounded. So this makes that I have, this is bounded, and since this V is compactly embedded in H, I use the fact that, I mean, I get directly that this is tight. So I get the existence of an invariant measure. Now, this is what I wanted to show you. So I have an invariant measure. We can prove that it is unique, but what would be interesting to prove is that it is unique just if you use a few modes. If you excite your equation just in a few modes, yes?
Are you talking about dyadic models, or are you talking just about standard stochastic Navier-Stokes with additive models?
I am talking about the shell model.
Please clarify what.
Yes, all this is for this. This is for this model. Yeah.
Which one?
So this is the model. So this is my nonlinear term. Yeah. This is my operator, and my equation is this equation, where my A is kn un squared.
Right.
Yeah. So
Okay.
all my results, I am not claiming anything for Navier-Stokes. This is for the shell model. Sure.
Yeah.
Yes.
The GOY model.
But
The GOY model.
But why cannot you include results similar result for the separation model because.
Oh yeah, for the what I
will
mean.
be more or less
Sure.
the same.
What I mean is that he was asking me if I was talking about Navier-Stokes or the shell model. Right? This is your question?
Yes, I was asking
Yes.
what
So-
you're talking about.
I am talking about, these results are all about the shell model. And here I was just clarifying the relationship with Navier-Stokes. All these results are on shell models. I hope it's clear for everybody. Sure. Because I am using heavily the properties of the nonlinear term, which are different from the Navier-Stokes.
The results which you just cited, they're true for
Navier-Stokes. But what I'm going to say later, in fact, what I'm going to say later, we don't know if it's true for Navier-Stokes. I don't know. Later, yes? So all I have said is not extraordinary because it's true also for Navier-Stokes. The
When
existence
you
of
mean
invariant
Navier-Stokes?
measure, yes?
Sorry. When you mean Navier-Stokes,
2D.
you mean 2D Navier-Stokes?
2D, yes. 3D,
No, yeah.
yes, but you're right. 2D. Yes, good that he clarified. This is all is for the shell model. But you're right, all this is also true for 2D Navier-Stokes. But remember that why I am trying to say something about the shell models is because their relationship is with 3D Navier-Stokes.
So you're considering shell model in 3D or 2D?
No, I'm considering shell models, but their correspondence is with 3D Navier-Stokes. The correspondence, the phenomenological correspondence. Yeah? So it's a minus. In a certain sense, it's a criticism. But the shell models that have been defined, and as I told you before, I am considering the GOI, because in the GOI, the only quantity which is conserved is the energy, as for 3D. Yeah? In this case, I am considering the GOI. Yes? So, we prove the existence of an invariant measure now. As I said before, we can prove the uniqueness of the invariant measure, but for now I don't need it. Okay?
You have a global existence but not uniqueness.
I have global existence and uniqueness when the viscosity nu is strictly positive.
Oh, okay. So
Sorry,
you are
I confused everybody,
Okay,
but
okay.
sure, I mean like for 2D Navier-Stokes and like even for 3D Navier-Stokes we have global existence, but we don't have. So here I'm considering nu strictly positive. Yeah? And actually here, given nu strictly positive. So I'm considering the viscous case. I don't know how to do things when nu equal to 0. It's very difficult, and the viscosity limit is extremely very interesting, but very difficult too. So here I'm considering
You have global uniqueness as well.
global uniqueness,
Okay.
the strong sense, strong uniqueness.
Okay.
I have additive noise. So nu strictly positive. I have existence and uniqueness of a global solution in P almost surely. The solution U is in continuous actually, 0T with values in H. Here I have to be careful. I will not write the other one because I have to be careful about the value of the process. So at least I am sure that my process exists and is unique and it is continuous with values in H. It has more regularity. Yes?
I don't understand now. It seems to me that when nu is 0, when you are an implicit case,
Yes.
you start with an initial condition which is smoother, you do get uniqueness.
Yeah, but this means that you are not talking about the weak solution. Yes, sure. She is saying that what I said before. So here, if nu is strictly positive, and I take the initial condition which is only in H, then I get the existence and uniqueness of a global solution. Okay? When nu equal to 0, if I start only with u0 which is in H, yeah, I can still have the existence of a global solution u which is L infinity 0t with values in H. I don't know if it is continuous, it's a problem. And so she is telling me, oh, but if we take u0 a little bit smoother in V, obviously I can prove, in this case, I can prove the existence and the uniqueness. It has been proved by Constantin Levin and TT, etc. I can prove the existence and the uniqueness, but it's not anymore. It's not anymore in a certain sense. You know, you are not proving the uniqueness in the class where the global existence is, in a certain sense. Okay? Yeah.
Don't you need L2 on V prime?
Sorry.
Don't you need that U belongs to L2 on V prime?
Which one? You?
U.
Do you mean as a consequence here?
Not consequence. If you are proving existence
You mean here? For the uniqueness?
of the solution, you need
No, you need only U0 in V.
derivative solutions should be where?
The unique solution,
Derivative
we
solution
proved it
in which
together.
state?
At this point we can prove the continuity 0t with values in H, intersection L2, 0t, actually L infinity 0t with values in V. I think this is what we prove. What did you say? L2, 0t with
Yeah.
values in V prime?
Right. The derivative. You need to define derivative. In which space is the derivative? Solution in H.
It would be under the assumption she had, it would imply that U prime belongs to L2 0 TV prime.
Yes, I mean, but the only condition I need is this. I don't understand your. As a consequence, you can have more. You can have U prime in another space. Sure, I mean, you can U prime will be in particular in L2 0t with values in V prime. Sure, yeah, but it's not an assumption. Yeah, you will get it automatically from the equation, etc. Yeah. Yeah.
Right.
Okay, so sorry about that. I am in the case, I am looking at mu strictly positive. Why we are looking at this? Because we are interested in, at a certain point I have to take the limit mu goes to 0, but, so for the moment I start with mu strictly positive. So I am not looking at this case. I showed it to you just because it's a nice result. It's a nice result that we didn't expect actually. So now, consider mu strictly positive, and I was able to, we were able to prove the existence of an invariant measure. I call it mu, because it depends heavily on mu. If we don't have viscosity, I am not able to prove anything about the existence of invariant measures. So mu, the one invariant measure, depends on the viscosity. Now, I will call the expected value with respect to this invariant, to the invariant measure that I defined here, I call it E nu. Each time you see E nu, it's an expected value with respect to an invariant measure. Okay? Now, this is not new. Let me just show you this balance law. It's a nice balance law that has been, used by a lot of people, in particular by Cookson, for example. I will give you another reference. We are able to prove that for every n bigger or equal than 1, we have this balance of energy. We call it balance of energy, yeah? Where the expected value here is with respect to an invariant measure. Here you see the viscosity. Here you see these nonlinear terms. This is the term from the noise. So you have a balance between noise, you are putting noise, the dissipation of the nonlinear terms. Let me just say 2 words about this term. This is an very interesting term in physics. It has a name. It's the dissipation, the dissipation rate. This mu. Let me write it as it is, and I will show you. So Kn square, right? Kn square, I can put it out. And then I have Un squared. If you look at this, now let me write it, the equivalent in the physical space. In the physical space, remember that this Kn squared is nothing else. So in the equivalent space, in the physical space, sorry, this is nothing else than mu. Let me write averages as averages, like this, just to show you. And this is the norm of u in V square. These averages. Now, let me tell you, for people that know about physics, there are a lot of, and I give you the following reference, Doreen, in particular, for example, is interested in this kind of quantities. It is known in physics that these quantities, at least they believe that this quantity, when u goes to zero, this quantity will not go to zero. It will go to a constant, which is strictly positive, which is surprising, yeah. And this quantity if you consider systems that are ergodic, you can say, oh, this is nothing else than nu, or let me write it like 1 over t, the integral between 0 and t, nu, the norm of this u squared in v. This is a quantity, these are time averages. So this quantity it's an interesting quantity. As I said, many people, so lately Doreen is interested in this, but there are a lot of works by Constantin and Foyas. So any information on this quantity is very interesting. Just to tell you one, for example, bounds from above and from below are very useful quantities to get for Navier-Stokes. When the limit nu goes to zero, obviously. Why I'm saying this? Another reference. I have to give all the references. So this is a balance law, but let me tell you about these balance laws. It has been proved, for example, this viscosity limit, but for other kind of problems, it has been used by Cooksin. If you look at his paper, but it's different from this because he uses the viscosity even in front of the noise. So in a certain sense, I can tell you what he's doing here. Cooksin, CPM, Communication Mathematical Physics, I think 2008. And he has others, but this is the last one, and it's an interesting one. I mean, he uses some kind of balance laws here in order for him to prove, but it's not new, that the deterministic 2D Euler equation has invariant measure, and he can write down some kind of invariant measure that comes from the stochastic Navier-Stokes. And let me just show you. So this is the balance law that we are using, and let me show you just the theorem that we are interested in. I think I have still 5 minutes, right?
Yes, 10 minutes.
I have 10 minutes, okay, 10 minutes. So what I wanted to say is that this, so still, remember that I am interested in this behavior. I am interested in shell models, the shell model that I have written before. So I am interested in these averages with respect to one invariant measure that I proved which exists of these quantities, and I would like to say something about its behavior with respect to P, yeah? Is it like this, and is this Cp, x zeta P, is it like a P over 3, or is it something else? So the problem is that these quantities, you have to take them, so these are all problems of scaling, etc. Let me just tell you something that Kolmogorov has defined, is that, I mean, you are not working anywhere. We are working under the condition that Kolmogorov has a scale, and he says that the scale, in a certain sense, there is it's called the Kolmogorov scale, and this is like nu to the power 3/4. This is the Kolmogorov scale. So we are working for turbulent fluids. We are working under the condition that this has to scale like, I mean, it's normal that the viscosity has to depend on the scale has to depend on the viscosity. So I am working under the condition, remember that my Kn minus is my R, has to be similar to nu to the power 3/4. So I have to work with nu, the viscosity nu, and n, which are my scales, but it hasn't to be anywhere, it has to have certain scale. So the viscosity has to be really small, so it has to be between an interval 0, 1. And my n has to be between n minus and n plus, and I'm going to define them here. So I am working in a certain rectangle which depends on the viscosity and n, and the relationship between, you know, this n plus here is such that you have this this limit here, which is it's equivalent to this one, the Kolmogorov correspondence. So I am working on this interval here, and I am going to define the following quantities. I'm going to define the zeta p plus, because I don't know if this limit exists actually. So I'm going to define the lim inf and the lim sup of these quantities, which are the 1 over n log in base 2. I'm using log in base 2 because I'm taking kn equal 2 to the power n. So I'm taking everything in the logarithmic scale, and I have this expected value. And this, the lim sup, minus the lim sup. Remember that I have my kn to the power minus. Yeah? I define these two quantities, and I will just give you another definition. We define now, remember that the nonlinear term had these quantities in the balance law. So I'm going to define this C3 flux as minus this limit when u goes to 0, but in the range of that rectangle as this quantity, when it exists, obviously. And I'm going to give you the following theorem. If you work in a certain range, the Kolmogorov range, in a certain sense, these are betas and epsilon that are, you know, you choose them. So we have the following, let me focus on the following theorem, the necessary and sufficient condition. This zeta 2 minus is larger or equal than 2/3, because I'm looking at the quantities when p equal to 2, if and only if this lim sup of this quantity is negative. Now, this lemma, this result is completely independent from the goal. It's a lemma that we can prove just thanks to the definition of zeta p plus and zeta minus. Let me just give you now, so it's a very general. Now I am going to apply it to the goal. I'm going to show you just what I can do and where I cannot do anything. If I assume that I have only, for example, the first 4 modes that are you know, excited, so sigma 1, sigma 4 are equal to this quantity, and all the others are 0 for n larger than 4, and if I assume that there exists a mu bar such that, and there exists a gamma such that this quantity is smaller than gamma, then on a certain range, you see, then this is for my goal, then I can prove the following. There exists a constant c depending on sigma, gamma, and plus, etc., such that this expected value is between these two quantities, and if I prove this, as a consequence, automatically I will have that this is true because of you know, you can plug in everything here. This is the main result. Now let me just show you that this is a result that has its limitation. Well, it is still interesting, but I am enabled. So if this condition is true, then I can plug this in the Goy model using the balance laws, etc. I can prove that, what is the pointer? That I can prove that this is larger or equal than 2/3. But I am enabled, we are enabled for now to prove anything, to prove that this is true for the goal. I have to assume that this is true. Yeah? So, let me show you just, maybe I have 2 minutes because it's very interesting just to show you something. Why it's interesting. Did I lose here? So let me just write down maybe the following quantities. The balance law. I wanted just to show you the balance law because it's interesting in itself. Let me write it. So remember, I have the goal, which was, you know, the sequence of ODEs solution for this UN. And now let me write down, if I define this epsilon n equal to kn squared I will nu, and then the expected value with respect to the invariant measure of un squared. And if I define phi n as kn expected value of un plus 1, un plus 2, this is the wrong, because I am working on the dyadic model. I can, so the balance law, let me write down the balance law with the energy. I will have epsilon n plus phi n equal to phi n minus 1 plus phi n minus 2. I think there is 1/2 here. And then I have, what is that? Okay. Just to show you. I think 1/2, it's 1/2, I am sure about the 1/2. You have just to substitute, because it's, so what I wanted to say, so we have this plus, you have sigma n star, and this is, I think, you have 1/2, I don't remember, for n bigger or equal than 1, and for n bigger or equal than 1, yes, and we have the following. You have the following initial condition, that phi 0 is equal to 0, and epsilon 0 is equal to 0. I mean, for n equal to 0, you start with 0. So the balance law, in a certain sense, it's an iterative scheme in a certain sense. And what we are just, this theorem is just telling you, I mean, we use this. What I wanted to say is that we use this in this, this is the balance law given in the iterative way, to prove that in fact there is a relationship between epsilon n and phi n. But under the condition, what I wrote there is nothing else than, in a certain sense, so this condition is crucial. See? This condition here is really, really crucial. I assume that this is true. But the problem is that I am not able to prove anything. So if this is true, then I go back to the balance laws, etc. I prove that this C2 is bigger or equal than 2/3. But what would be interesting is, can we prove something similar just using the GOI? And this is very difficult. And to be honest with you, this GOI is very difficult, so I am trying to work on another model, which maybe the relationship here is a little bit easier, but so far I didn't go so very far. But the model that I'm working on now, because it might be easier, is the following. It's the following. It's dun plus. So this part is similar. It's really similar. dt equal. It's the nonlinear part which is different. The nonlinear part is much easier than this one. So this is kn minus 1 square un minus 1 minus kn square, and here you have un plus 1 dt. This is plus, and now I have an additive noise. And actually, so this is like a dyadic model. It has the similar, for the nonlinear term here, it has the similar property of the Navier-Stokes of the bu equal to 0. But here I take sigma n equal to sigma for n equal to 1, and I am taking sigma n equal to 0 for n larger or equal than 2. So I am just exciting with the first mode. We can have similar properties, but I can write you the difference here. You see, my balance law here will be completely different. I will have the following. I will have epsilon n plus phi n equal to phi n minus 1, with phi n a little bit different, but and I will have 1 sigma n square. And I use this in the real value. It's not complex valued anymore. But there is hope that maybe with this model, we will be able to weaken a little bit this condition. I mean, to be able to prove something. This is an assumption which is strong. I mean, you assume that this is true, and then you prove something. But is this provable for the Navier-Stokes? For the model in itself, it's challenging. I think my time is over. Thank you very much.
Thank you very much. So, we have questions and comments?
You could try simulate.
I would like to have suggestions, in fact, for this.
I'm suggesting to try to simulate and see if something like this inequality shows up.
We have simulations.
And
Yes, so I didn't get so in our first paper, Barsanti, who is the computer guy, he simulated in fact this quantity, and there is hope that in fact, you know, that quantity is like 0.66, so it's not 2/3. I mean, it's a little bit larger. Is it 0.7? It's hard to, you know, so what are you going to say? You simulate, you say, oh, there is hope, but then you have to prove it rigorously.
yes,
Yes, so we simulated it. So there is hope that what we are saying is true, but then we have to prove it rigorously. It was not clear from the simulation. For sure, I mean, he did, I think, 10 simulations, and it is still a big simulation because it took him a long time. But
It's in dimension 3.
no, but I'm talking about the shell model. We have simulated the shell model. So he has simulated shell model.
Shell model in 3.
But what do you mean by 3? Shell model is shell model in 1 dimension. I mean the GOI. He simulated the GOI model, sure.
Which models? GOI models?
Yes.
Models 3 dimensions.
Yes. But even if you get a simulation, I mean, we have the simulation. It's not. I mean, once you have a simulation which is somehow more closer to 0.7 than 0.66, still you have to. I mean, we have a proof of this. But now my point is, this condition that I have, if you assume this, then you have that the C2 is bigger or equal than 2/3. Yeah. So now, I would like to have some suggestion of. I mean, we don't know how to do it. Is there a hope to have this condition weakened or prove that this condition is true for the GOI? It's not easy. I mean, from here, you don't get. I did some computation, even though I'm trying to do some computation for this. It's not easy because it's not clear. But a big breakthrough would be to say, oh, from here I compute and I find that that condition is true. This would be great, but I don't know how to do it.
There are many other duadic models, various versions. There's one of Sinai and Dannenberg, Natasha Pavlovich did a lot
This is
of
the one.
work.
This is the one that Natasha Pavlovich and Friedlander. This is the one that we are studying.
But then she worked with Susan Friedlander on
Yes.
other models.
Other models than this?
Yeah.
Yeah, you think, I mean, the one that I looked, you're right, this is a model that has been studied in the deterministic case by Friedlander, you're right, and they are working hardly on it. I mean, it's a current research for people in the deterministic case. But sure, this one, but for now, I don't know, I mean, so all your suggestions are very welcome.
Class of nu, how does it scale? How does it scale n plus of nu as a function of nu?
Which one?
N plus.
N plus. N plus, how does it scale in function on nu? I don't remember the details, but did we use that in our paper? No.
I think you gave the explicit expression.
Yeah, but he's asking the relationship with the.
Also,
I gave maybe one, but it's in our computations.
there is a bar missing there. Right? It's one.
This one. Yes. Yeah, it's so Kn, because remember that my Kn is 2 to the power n, so it scales like minus nu to the power minus 3 over 4. And this is, I mean, we took it from, this is physics. We don't have anything to do with it.
Okay. And so, okay, can you back to the slide with it?
Forward, you mean?
No, not the forward. Yeah, just to the one with the second. Yeah, the one with the inequality, with that smaller than gamma. Just
Yes.
yes. So there is n plus of new bar, I guess. Yeah, for every new n.
This gamma is fixed. Actually, you
there's
can.
a bar missing, I guess, no? And
This gamma, I mean, you're right. This is, I can make it more stronger. I can, instead of gamma here, I can take gamma nu. I mean, I can, this is one condition. You're right, I can.
No, but I was going to say, okay, I mean, this inequality can be proved somehow for some n. No.
From the equation, this is, I would love to do it,
no,
yes?
but not for, I mean, for n equal to just, if you want this just for n equal to 1, this is fine. You can prove it, I guess. No? So
But you have to, so you are saying,
you want to
okay.
be uniform in n up to n plus of new bar.
But no, it's not, if I didn't have the 2/3, it's, you have to be careful. This is 2/3.
Yes, you want this to have uniform in n. I mean, the gamma should not depend on n or nu up to n, for all n up to n plus of new bar, no, isn't it? This
The
is
last
what
line,
you need.
it should be.
Okay, the bar is here, but I was just wondering. I mean, you can prove it for all n up to.
N plus, no, it's.
No, you cannot prove it up to n plus, but.
I don't know how to prove it.
Yes.
I use it.
No, but not. Yes. But I guess you have tried to prove it.
The problem is that no, it's not to prove this. The problem is that since this is related to an equation, I would like to take an equation and to work with the equation, blah blah blah, and then
Yes.
from the equation get this condition.
Sure.
I am not able to do that.
Sure. No, but I was just wondering. Okay, maybe you cannot prove this inequality up to nu plus, but maybe you can prove it. I don't know, up to log.
I cannot,
Log of
not
nu
even the
plus.
first one, to be honest with you. Maybe I should, I don't know how to prove it,
No,
not even the
for-
first one.
For an equal to 1.
No, I don't see how you,
So
because,
this just, I mean, for n equal to 1, this is just.
no, because this is, this is square here, this is un plus 1, un plus 2, then you have to make it, to put inside the 2/3, and you have no information on this. I mean, you don't have any information on this, so you plug it
For
inside.
the first mode, just to get uniform in nu, this is okay. Okay.
But yeah, I understand what you mean.
I mean, what
To be honest with you,
what
I
mean
went
is
there, yeah.
that you need a bound which is uniform in n and nu.
It's not uniform in what I said. You're right. I wrote gamma here, but you can have even gamma nu. It's not necessarily uniform in nu. It has to be, so it doesn't.
And nu is small, so if you're
Exactly, yeah, exactly.
It doesn't happen.
I mean, you are not allowed to have gamma over nu, but you are allowed to have gamma multiplied by nu. Yes,
It's
but
clear. Okay. I was just
But I
wondering
didn't
if it
try-
was hard the uniform bound over the modes, but you say no, it's even hard in nu. Okay.
yes,
Okay, thanks.
I don't know. I'm trying with this model because this shape is easier. It's nicer, but still it's not obvious. Maybe people that are working in this maybe understand models, or I don't know what they are doing. I mean, I have to be inspired by probabilistic approach, or I don't know. I have to be honest with you. I don't know what to do now. This
I
is
have a suggestion.
yes.
Leave it as it is. In 10 years, it will become famous as Bessaih's conjecture. You will.
$1 million.
$1 million growth.
Okay, so with this very happy
Yes.
question, let us finish today's session, and I just wanted to remind that we have